In this video, we consider two versions of the Floyd Warshall algorithm. One finds us the transitive closure of a graph, and the other finds us the shortest distance between any pair of nodes. Actually, it's Warshall's algorithm which finds the transitive closure, and Floyd's which finds the shortest path, but both are often referred to as Floyd Warshall because they are very similar. What is transitive closure? It tells us which nodes are reachable from which other nodes. The transitive closure of a graph G is a graph that contains an edge from node X to node Y if and only if there is a path from X to Y in G. For example, we can see there is a path from A to D via B, so we add AD. We can see there's a path from B to C via D, so we add BC. And we also add an edge from each node to itself, since every node is deemed reachable from itself. This is actually referred to as the reflexive transitive closure, although it's normally what we refer to when we talk about transitive closure. Transitive closure has theoretical applications in graph theory, and in real life can answer questions like, can I drive from city A to city B? Does person X report to person Y directly or indirectly? Does job A need to be done before job B can start? In a spreadsheet, if you change a cell, do you know which other cells you have to update by modelling it using a transitive closure relationship? Floyd Warshall solves this using a triple nested loop. It asks, for each node k, can I travel from I to j via k, where I and j are all other pairs of nodes? This can be stored as a matrix or a graph. In the adjacency matrices shown, an edge from one node to another is represented as a 1, with a 0 if no edge exists. If a graph is unidirectional and connected, the transitive closure will necessarily be a complete graph plus all of the loops. Since every vertex is reachable from every other vertex, an edge will exist between every pair of nodes in the transitive closure of G. The algorithm has two parts. First, we copy the matrix based on the existing edges. We start by adding edges from each node to itself, since each node is reachable from itself. Then we consider every other node as a stepping stone between every other pair of nodes. Note carefully the order of the variables here. Just as one example, we can see that if k equals 1, which is to say node B, there is a path from A to B and then from B to D, which means we can add an edge between A and D. We carry on doing this until we get the complete transitive closure. Floyd Warshall can also be used to find the shortest distance between all pairs of nodes. This is different to Bellman-Ford or Dijkstra, since it finds the shortest distances between all pairs of nodes. The downside is that it takes longer and is harder to reconstruct the shortest path given the shortest distance alone without making a small modification. We use a distance matrix rather than an adjacency matrix. Again, let's step through the code. In the initialization phase, we set each distance from a node to itself as 0 and the rest to infinity. Then, in the second part, we consider again each node k as a stepping stone between each pair of nodes I and j. But this time we ask, is there a shorter path from I to j via k? If so, then we update the distance value from I to j with this new value. Again here, we can see that at the moment the distance from A to D is infinity, that bottom left value under the 5. But we can see that to go via B, from A to B is 1, from B to D is 1. Add those together, you get 2, which is of course less than infinity, and so we can set the distance from A to D as 2. We do that over and over until we have all of the shortest distances you can see. Note the slight change in the code. You can use the minimum function if you like, and this is quite a common feature of dynamic programming design patterns, which is what this is. It's something we cover more in Unit 4, but in general it's the idea that we build up a solution by saving results from smaller problems and using them to solve larger problems. For example, node B gives us a shorter path from A to D, which in turn gives us a shorter path from A to C. So there you have it, how Floyd Warshall algorithm finds us the transitive closure or the shortest path using quite similar algorithms. Note the dynamic programming design pattern, and if you're reconstructing this, be very careful with the order of the variables.